everyone for joining us for our C2M2 Center for Connected Multimodal Mobility Distinguished Speakers series. We're really excited today to have Mashrur Ronnie Chowdhury, who is our center director, as our featured speaker today. For those of you that don't know, Dr. Chowdhury is the Eugene Douglas Mays Professor of Transportation at the Glenn Department of Civil Engineering in Clemson. At Clemson University. He's also a professor in the Department of Automotive Engineering and in Computer Science at the School of Computing. He's the founding director of our USDOT Tier 1 University Transportation Center, as well as the co-director of the Complex Systems Analytics and Visualization Institute, C-SAVI, located here at Clemson. His research focuses on transportation cyber-physical systems, security, navigation of connected and automated vehicles through in-vehicle sensors, and external connectivity with digital infrastructure. He looks at heterogeneous wireless communication for security and distributed machine learning on the edges, as well as other edge computing applications and safety risk analysis for autonomous vehicles. In a mixed traffic stream. Dr. Chowdhury has published over 100 peer-reviewed journal papers, 85 peer-reviewed conference proceeding papers, 4 textbooks, 9 book chapters, and 7 research articles in professional magazines. He's also developed several software packages for connected and automated vehicles like AutoNavi, CVDEP, CVGuard, POSH, PSM Gen, which we're going to learn about today. And all of these products can be found on our website at cicus.clemson.edu/C2M2. That's also where you'll find a recording of this presentation, or you can find it on our YouTube. And we thank you for joining us.
Thank you, Charlotte. So welcome to our seminar today. So our topic is pedestrian safety. So specifically, we developed personal safety messages for pedestrian that can impact pedestrian safety in a very positive fashion in a connected vehicle environment. And my contact information is on this slide. And also, as I proceed forward, I will also cite some documents where you'll find more detailed analysis and results related to pedestrian safety applications. So our research motivation. So our center undertook this project because of the severe problems we are facing with pedestrian fatalities. So number of pedestrian fatalities increased by 53% between 2009 and 2018. And pedestrians account for 17% of total road fatalities in this country. And on average, 60,000 pedestrians are injured per year in the US. So the statistics are green for pedestrian safety. So that motivated us to see if transportation cyber physical systems can help in combating this problem that we are facing. So this is basically a system level view of our application. So we have roadside cameras. So at intersections, it's a very low cost cameras. So, and that camera images are sent to roadside infrastructure. In our case, it is so we have it connected testbed on Perimeter Road in Clemson. So on every several hundred feet, we have this type of infrastructure. So we have a radio that will broadcast wirelessly the information like alert or any driver information or pedestrian information. And also we have a computing device so that can compute the data that we are receiving from roadside camera. It can run algorithms, and then it sends to the radio. In this, we are showing a DSRC radio, but we can use any communication medium for this application. So that once it is computing pedestrian safety alert, So it will send to connected vehicles or to any phone app. So if the cell phone app is running our pedestrian safety application, then you can directly get that warning. Now, in terms of data, so I showed that we are looking at the video image uh, from the intersection. We are, in this case, we are looking for pedestrian. And then also we are receiving data from connected vehicles. So this is showing the connected vehicle data. So we are just receiving data on where the connected vehicles are, what the speed of the vehicles are. So we use those two pieces of information, camera data and connected vehicle data, to identify the risk of pedestrian crash, and then we warn the vehicles as well as the pedestrians. So this is basically the high level view on our test bed. So the contributions of this research, so it's a vision-based approach to generate personal safety messages. We are following the Society of Automotive Engineers J2945 standard, so which is for vulnerable road users, pedestrians, bicyclists, people with disabilities. So we are purely following that vulnerable road user standard from SAE. So in the vision-based approach is very low cost. So as I mentioned earlier, any type of low-cost camera can run our application. So the second primary contribution is that our safety alert system using the pedestrian safety messages are able to reduce the risks of possible vehicle-pedestrian collisions. So we did a test in real world and we found we are getting very encouraging results. Now, research approach. So this is like a block diagram of the task flow. So we have a vision-based, we are first detecting, pedestrian. And then once we detect the pedestrian, we are localizing the pedestrian. And then we are tracking the pedestrian. So we are computing speed and direction. And based on pedestrian location and pedestrian tracking, we are generating personal safety messages, as I mentioned earlier, following exactly the SAE standard for vulnerable road user. So after we are generating these messages, we are using these messages to, and so pedestrian safety message as well as data from the vehicles, where the vehicles are at the intersection. We are generating this safety alert. The safety alert is based on collision risk assessment. So we are assessing the risk of crash between a pedestrian and a vehicle. In this case, we are using connected vehicles. And we can then broadcast the information using the radio I just showed earlier. It can be any type of radio, but in this our test, on the test bed, we used DSRC radio. We can use 5G, any communication medium to do this. So then we can alert the vehicles. So we tested here, you can see that our alert was showing the pedestrian ahead to slow down or stop the vehicle. And also we can alert the pedestrian through their phone if they're running our pedestrian safety app. So first, now I'll go through the steps I just mentioned in the box diagram. The first was pedestrian detection. So this was the image from our low-cost camera. So 720 by 576 pixels. We resized the image to 640 times 480 pixels. The reason behind is the processing time or processing resources. So we ran different pixel sizes and we found that this is the optimal pixel size in terms of processing resource needs. So that was after doing a lot of testing, we determined that this is the optimal pixel configuration that we should use. Now, then we use a vision-based deep learning model to actually detect the pedestrian. And and I will shortly show what deep learning model we used. So deep learning is a type of artificial intelligence model. Now the output from the deep learning model is this abbreviation CP. So I'll just quickly go over it. So C means that whether a pedestrian is detected. So yes or no. Now the P is confidence score of the detected pedestrian. So how sure it is that this is a pedestrian. It comes as an output from the deep learning model. Now this is the third one, PXPY is the pixel value of the x-axis and y-axis from the bottom center pixel of the bounding box. Bounding box is here showing that there are two bounding boxes here. We're showing one bounding box. So each pedestrian, when we are detecting a pedestrian, we are putting it in a bounding box. So that bounding box, we are computing values related to the bounding box, as I mentioned, PXPY. So where the x-axis and y-axis on the bottom center pixel of the bounding box. And then PH, this is the PY, this is the height and width of the bounding box. And once so this is coming as an output from the deep learning model. So once we get this, then we have this information, but we improve the detection accuracy with a non-max suppression method. So for example, what could happen that one pedestrian could be in two bounding boxes. So we want to make sure there is a one-to-one relationship between bounding box and pedestrian. So we use a non-max suppression method. So intersection over union. So that's what we did mathematically, and the detailed description, I will show you some documents. You'll see that how we did that bounding box separation. So through this non-max suppression strategy. And then once we do the final output image in 640 by 480 pixels, so we very accurately detect the pedestrian on the crosswalk or anywhere at the intersection. I'm trying to go to the next slide. It sometimes gets slow. So now we saw pedestrian detection. I'll go back one slide. So now, so after pedestrian detection, we need to determine where the pedestrian is. So what we did from the camera image, we did a perspective transformation of the image. So what it means that, so it initially the camera looked at it from the camera angle point of view, but we transformed the pixel coordinates. So we looked at the pedestrian from the top view. So this is looking at the top view. So now after we did that, then we converted the pixel coordinates, which is came from our camera image. So we transformed it to real world coordinates, so in latitude, longitude. That's the localization. Now the next is pedestrian tracking. So this is showing that how we track the pedestrian at a high level. So yes, so you see that we have correlated the predicted pedestrian bounding boxes of 2 consecutive frames. So every 1/10 of a millisecond, we generated an image. And from that, we have the exact location information, latitude and longitude for 2 consecutive bounding boxes. And based on that, we calculated speed and direction of a pedestrian between 2 locations. So we identify the path of the pedestrian. So now we have the location, we have detected the pedestrian, and we have determined its path. So then we generated the pedestrian safety messages following the SAE standard. So you see the 2 standards I have here. So J2945. So that's a basic standard for vulnerable road users like pedestrians. But it is linked to the SAE J2735 standard, which is associated with the connected vehicle basic safety messages. So when you look at the pedestrian safety message standard, they will always refer to the basic safety messages because some of the details are coming from the SAE J2735 or basic safety messages. So they are very linked. So these are the data items that has to be transmitted 10 times per second or every 100 milliseconds. So message ID, message count, speed, elevation, temporary ID, you ID the pedestrian. So pedestrian 1, pedestrian 2, depending on how many pedestrian you have, and you have to track that particular pedestrian throughout its journey at the intersection. You get latitude, longitude, timestamp, personal device user type, so and then positional accuracy. So you have to first determine initially what is the accuracy of the method, in our case the vision-based system detecting pedestrian. So we have to start with an initial accuracy and then heading, so the direction the pedestrian is moving. So using our video image, we have to calculate all these items following exactly the format prescribed in the SAE J2945 standard. So this is what we generated. So after we analyzed the data, so we generated, the earlier slide I showed different data elements. So this is a sample of data elements. So I'd like to point out in the green, you see 111, that is referred to a particular pedestrian. So we ID'd it as 1, and 2 represents another pedestrian. So in this example, I'm showing 2 pedestrians. So this data, PSM packet 1, after 100 milliseconds, your packet 3 will be generated. And then after 100 milliseconds, this packet 5 will be generated because it is related to pedestrian 1. Similarly, we are generating messages for pedestrian 2 every 100 milliseconds. So now the device type here in this pedestrian that we are detecting, then message count, lat long, elevation above the sea level. This is the initial accuracy which we determine based on testing, velocity of the pedestrian, and the heading direction of the pedestrian moving. So now, first we detected the pedestrian, localized the pedestrian, identified its path, but the next was to test it on a pedestrian safety application at a system level. So we went to the US DOT sponsored National ITS architecture. They have many connected vehicle applications. So one of the applications is pedestrian in signalized crosswalk warning. And we tested this system, this application, on our connected vehicle test bed at Clemson University. So now pedestrian safety alerts are based on time to collision. So this is the initial location of pedestrian at time t, location of vehicle at time t. The epsilon is the distance between the vehicle and the pedestrian at collision. And then based on that, we formulated this equation, and we solved this equation, quadratic equation, and we had 2 values of t after solving this equation. So, and we took the minimum value of t. T is the time to collision. And the formulation of the detailed equations and solution is in the citation I will show later. But basically the thing is we did a computed time to collision. So from the location of the pedestrian and location of the vehicle and the velocity of the pedestrian, velocity of the vehicle. And we computed the time to collision. And all this information came from the pedestrian safety messages and vehicle safety messages. I'll just go back. So that's an important point. So all the data that we are generating, so pedestrian is providing us PSMs, and vehicles are providing us basic safety messages, basically position, location, heading. Now, the evaluation of the system. So this is the experimental setup. We little bit talked about it earlier. Again, we are showing a little bit more detail. So this is our roadside unit, and we have the radio, DSRC radio, and also we have a data processing unit, Jetson TX2 NVIDIA Pascal unit. So we have these devices in of our roadside units along perimeter road. So it is near the traffic signal. So we have this infrastructure close to different intersections at perimeter road. So, and now roadside camera is sending video data. So the video data in our application, we are sending it to a wired communication. So we are using a fiber optic cable to send the video to this roadside device. From the camera to here, it's coming through a fiber optic cable. And then, so it is generating so it's locating the pedestrian, it is finding its path, and it's generating the safety alerts. So when it's generating the safety alert, it is sending to connected vehicles through the radio. That's the purpose of the radio. Now, in our case, we did it with DSRC. We can use 5G as well. We need some low latency communication technology. So 5G will be a good option to undertake. And also we can send the safety alert to the pedestrians. Now, the pedestrians do not have to carry any devices. So we don't have to have to make the system work. The main thing is to alert the connected vehicles or somehow alert the approaching vehicle. So, the basic premise of our research is that we are not requiring pedestrians to carry any device. So, for example, like they don't right now there is a concept that you can carry a DSRC radio. There is one for pedestrians, and if you carry that DSRC radio, then you can communicate with any other DSRC radios. But in our case, we don't need anything actually to make this safety system work. It's just a video camera and our algorithm running. It will do it, and we can alert vehicles, approaching vehicles, that there is a risk of them being involved in a pedestrian vehicle accident. So one motivation was that we don't require pedestrians to carry any device. And so you see the dash line means we are sending data alert through wireless communication. So now the pedestrian detection model, in the earlier slide, I mentioned that it is a deep learning model. So we use the yellow V3 because we did an evaluation of different models available. So yellow 3 is an object detection model, and we found that its accuracy is good, very good. And so we use the yellow V3 deep learning model. Initial weights for this model, we derived from the common objects in context or COCO database to train the yellow V3 model version 3. Now we evaluated in 3 scenarios, environmental scenarios, rainy, sunny, and overcast. Now we can evaluate at any other environment, but in this case we only use 3 different weather conditions when we are doing the field tests. So field data collection, we collected 1,300 images, and we retrained. So I mentioned that we trained initially with COCO data set, but we retrained with 900 images at a couple of intersections on perimeter road. And we tested 400 images for detection accuracy. So here is some evaluation results. TP means true positives, FP false positives, and FN is false negatives. So you see that we have in the sunny weather 164 true positives, 4 false positives, and 2 false negatives. So, and you can see that a similar trend observed for other weather conditions. So if I use the true positive, false positive, and false negative, and I can just put in a formula to calculate precision, recall, and map. So I see that they are pretty high. So precision was over 97%, recall was over 97%, and the map value, which is used to calculate the efficacy of or accuracy of a deep learning model, we also found it to be high. So the original yellow model had a lower object detection accuracy. So what we found when we recalibrated used in our model, it was pretty high than what we have seen in papers. So now localizing the pedestrian. So we have to be very, very accurate in locating the pedestrian to show that how our method in identifying pedestrian through the pixel, analyzing the pixel will work against GPS units. So we use to find the ground truth for the location of the pedestrian. We use the global navigation satellite system. Now we use 4 satellite data to locate the pedestrians. In addition, so it can also, based on the relative position of the satellite, it can also give some errors, but we corrected it. So we use a correction through an online service, and then we use surveying equipment, total station, to make sure that this is a it's a defensible ground truth. So we use OPUS to correct the navigation satellite data, and we determine the true location of pedestrians. So for this experiment, we use different direction and different data points. So for east-west, we had 88 observations, west-east 59, north-south 39, and south-north 39 observations. So where we determine, we compared our satellite-based location with the GPS location that is provided in the DSRC units. So in terms of pedestrian localization, as you can see in all of the 4 graphs, and we are showing x-axis number of observation and y is root mean square error. That and you can see that in each direction, either it's east-west or west-east or north-south, south-north. So vision-based path, so pedestrian alert safety system, that is our system that we developed. So in the green, so you see that, and the DSRC-enabled pedestrian handheld devices that that is available in the market. We found that we are always much better in terms of the error. So our error was much less than the GPS-based DSRC radios. In all cases, in all directions. So now looking at average, so average root mean square error. So you see that in each direction, so we are very low compared to the DSRC-enabled handheld device. So you can see the comparison. So ours only 0.31 here compared to 1.80. West is direction 2.23, where ours was only 0.31 root mean square error. So so we are doing pretty good in terms of using the DSRC radios, which uses GPS units. So our vision-based system worked out very well based on our evaluation. It's very important that you're able to locate the pedestrian accurately. Now the pedestrian tracking, so there's 2 items here. So you are determining the direction of the pedestrian and the speed. So if we keep the direction constant, then we'll see that in terms of detecting speed, we are performing much better than DSRC based device. So DSRC based device is giving us 0.78 in terms of root mean square, but ours is 0.43. So in every case, east-west direction, west-east direction, north-south direction, south-north direction, ours performed much better. Our vision-based pedestrian alerts safety system, all our pass always performed better. So now we are looking at a system level evaluation. So we tested, before we tested different components. So we tested the tracking part of our system. We tested the localization part. We tested the detection part. But now we are combining everything, and we are looking at the efficacy of the system as a total application for pedestrian safety alert. So as I mentioned, that everything we are doing following the SAE standard, and also according to the SAE standard in terms of delay. So the time you send the video data and the time an alert is received by a pedestrian or a vehicle must be within 100 milliseconds, because it's a safety application. So we have to do it very quickly. So we have to make sure that we are under 100 milliseconds. And it's a J2945 standard. So now at a system level evaluation or experiment, so you see that this is showing the trajectory of the vehicle moving, and A is the vehicle pedestrian collision location. So based on the time to collision, in this example, this is where the accident will happen. If our prediction of pedestrian path and the vehicle paths are true, then this is where the accidents will happen. So again, it's based on time to collision. And location B, so when the vehicle, so you see that we determine, our system PAS determine that there is a critical risk of an accident between pedestrian and the oncoming vehicle. So it will instantly send a warning to the vehicle. So this is where the vehicle was when we determine that there is a risk of collision. So through a risk assessment. And then once this vehicle receives that warning, it can, so sees the location, it stops. So now this figure is showing where the vehicle will stop. So it started, this is the prior, once it received the warning. And this is the after picture. The right side is the after picture. So it stopped before the accident. So because it got, we tested that whether the warning is enough for a vehicle to come to a full stop. How much time to take the braking and receiving the information. So it was able to stop before the crash. So in terms of latency, so first is the computational latency, and communication latency is the second part of the latency. And then the total maximum latency that combines both the communication latency as well as computation latency. So it has to be below 100 milliseconds. As I mentioned earlier, so we are doing computation. We have this TX2 computers, so that is running the algorithm. So in the computational latency includes the data coming from video to the roadside unit, and roadside unit is processing the data and completing the processing of the data and generating the safety alert. This total time, the image received by our roadside unit, it processed the data and generated the alert. So that is the computational time or computational latency. And the second part is the communication latency. It includes when the alert is generated and then it's received by the vehicle, connected vehicle. So alert is sent from the roadside unit and received by the vehicles or by the pedestrians. So that is our communication latency. So this total communication latency plus communication, computational latency plus communication latency totally must be below 100 milliseconds because it's a safety critical application. And as you see that our minimum latency on different experiments, we found that computational latency is 54 milliseconds to generate the alert, and the communication latency, the time it takes the message to go from the roadside unit to the vehicle is 2 milliseconds. Using DSRC in this case, we tested communication only with DSRC, and the maximum is 64 milliseconds, and the communication latency maximum was 17. So average was 56 for computational latency and 4 for communication. As if you add these two, like for minimum, maximum, average, all are below 100 milliseconds. So we are fine in terms of SA standard. So, and this, the graph below is showing that, so I have this range of end-to-end latency. So between 56 milliseconds to 58 milliseconds, we have 10 observations. Between 58 milliseconds to 61 milliseconds, 61 observations. From 61 to 64 milliseconds, 80 observations. All are below 100 milliseconds. If you look at the end point here, so we see one data point where the latency is over 80 milliseconds. So we have to make sure that, okay, we cannot put one vehicle at risk, but this was also below 100 milliseconds. So when we analyze the data, it was over 80, but under 100 milliseconds. So, so for this extreme case, we were still under 100 milliseconds. So yeah, the x-axis range of end-to-end latency, the total latency, and then the y-axis is the frequency, as I explained. Trying to go to the next slide. So all our tests were done at intersections on our connected vehicle test bed. So our so this is a connected vehicle test bed, and we are just highlighting some of the infrastructure. So we have this test bed. So this whole about 3-mile road on perimeter road, these are connected vehicle corridor. We do tests with autonomous vehicles and connected vehicles on this corridor. So we have radios, we have our own LTE stations. So you see the 2 LTE towers, base stations. We have DSRC roadside units. We have our own Wi-Fi access points. We have cameras, and also our signals are connected. So if you have a connected vehicle, you can get the signal data, signal phasing and timing information directly to your vehicle, because these are all signals are connected. So, but one unique thing that that is enabling us to do this, like the pedestrian research or autonomous vehicle research or connected vehicle research, is not what we have on the road, but the back end. So the back end. Because I think that's the most important part. So we'll have 5G radios, we will have DSRC or LTE radios. But the thing is how you analyze the data. So we have been working on this for a long time. We are focusing on the back end. So how you process the data, how you distribute the data. So in addition to your communication, that is we need to study that, and we do that. But we looked at how many layers of computation we need. What is the optimal level of computation? So what type of infrastructure we need? Because these are kind of following the big data structure, the data that we'll get from connected vehicles, automated vehicles, different kinds of data. Sometimes it could be huge. As we have more connected vehicles, so it will be a challenging task to manage that data. So we looked at how you can process the data, how we can save the data. So how we archive the data. So we use different types of servers to manage the data. And also we are using how we distribute the data. So we are using like a broker system, so to manage the data. So we have a set in our test bed, we have a sophisticated broker system that is managing the data distribution for our connected autonomous vehicle data. I'm going to the next slide. So that's where we are doing our testing, including our pedestrian safety application. So this is showing that our research on pedestrian safety. So we are constantly monitoring. This is this intersection. This is actually a live streaming. That's what is going on at this intersection now. So whenever a pedestrian is going, we can detect it. And if you have a connected vehicle, we will warn you that that if you are in the path of a collision path with the pedestrian. So we constantly get real-time feed and we analyze the data. Now here we also did something that would be helpful for implementation of this system in real world. You see that the first I'm showing here the right upper corner, so that you see that we are not compressing the video. But if you do not compress, so the data video, I'm trying to go back to that. Okay, so now we are not compressing the video. So, but imagine, so when you're sending video from the camera to the roadside unit, you might be using wireless communication. So then video will have, if you have constantly detecting and you're sending data every 100 milliseconds, it might be an overload on your communication system. So what we are doing, we are compressing the data using dynamic lossy compression technique. So based on the weather conditions, it will compress in different way. So sunny condition, it will compress the data in a way that we can achieve a certain level of accuracy. So the data that we are sending is a compressed data, but we are making sure that due to compression, the video quality definitely goes down, but we save on bandwidth, but it is not exceeding a certain level. So that's where we are also running lossy compression with our this pedestrian safety alert system on our perimeter road test bed. So this is the highlight of the lossy compression that we are doing. Is error-bounded lossy compression strategy. So we are dynamically changing the video compression level depending on different environmental conditions. In order to maintain a certain level of accuracy, we wanted to make sure that no matter how much compression we do not exceed, so we do not go below 97% in terms of detection accuracy. So if you look at the flow chart, so video is coming, and then we are compressing the video on a roadside unit. So using the peak signal to noise ratio. So that, we determine that we have to maintain certain signal to noise ratio based on the environmental conditions. We are getting data on environmental conditions from our video too. So we are classifying whether it's rainy, it's dark, or it's sunny. So based on the environmental conditions, it is compressing the data in a way that we can maintain a certain threshold peak to signal to noise ratio so that our accuracy doesn't go below 97%. So then we send the compressed video to our edge computing infrastructure, or in this case, it's running on our TX2 computer. And and then we use that, the compressed video to detect the pedestrian. And we already, you see the upper here, we calibrated the detection model based on different environmental conditions. So we trained our model based on different environmental conditions. And also here, see, we also storing some of the data for later analysis. So it will not be used for real time, but you can use it for later analysis. So as I said, that we have an extensive backend infrastructure. So we know, like, we are archiving data, and some data we are using for real time. So, and a lot of the things that we are doing on a test bed are actually, I think, are best practices, because we have been doing this for quite some time, how to develop the backend digital infrastructure. So now look at the table on the right. So the pedestrian detection accuracy, where we did not compress the video, we just send as is. And also we did not calibrate based on the different weather conditions. So you see the accuracy with just sending the video. So you need definitely higher bandwidth. So in baseline case, when we didn't compress 98%, our case 97%. Now in heavy rain, it was from baseline, it was 83%, ours was 97%. But you see that we could not reduce the bandwidth too much. Otherwise, the quality will go, the signal to noise ratio will go to a level that it will not be able to be accurate. So that's why we did not, we were not able to save bandwidth, but we improved our accuracy because we calibrated based on different environmental conditions. But let's look at the normal condition. If we do the error-bound lossy compression, you see that the accuracy is very close, the detection accuracy, but we save bandwidth by 18 times. Can you imagine that we can save the bandwidth by 18 times by compression? It's a dynamic compression. At the same time, yeah, our accuracy is very similar to what you do without compression. And we did it for different weather conditions: medium, dark, high, dark, light rain, medium rain, heavy rain. And we found benefits of our compression strategy in every single weather conditions. In every weather condition, we found we are benefiting from dynamic error-bound compression. So in few conclusions, so our estimated location and speed of pedestrian, that will give you a risk profile of the pedestrian being in an accident with a vehicle. So it was giving higher accuracy than any DSRC-enabled devices that are available commercially. And also our speed information through the vision-based system is very true to the actual data, the ground truth data, very close to the ground truth data. We also satisfy the computational and communication latency requirements, which is below 100 milliseconds, as I showed earlier. So it is ready for real-time application. It's a safety critical application. So we have to be under 100 milliseconds, and we achieve that. And also, yeah, I'm going back to, okay. So we developed at the system level, the pedestrian collision warning. So we did different types of tests in different weather conditions. So ours was giving warning and the right time, and the vehicles are able to stop. So we potentially saved accidents, pedestrian vehicle collisions. If we implement that in real world, I see a major contribution towards pedestrian safety. Now, we use just pedestrian walking on the crosswalk at the intersection, but we can use, extend our algorithm for other types of vulnerable road users, such as bicyclists, motorcyclists, people on wheelchairs. So now the last point is a very low-cost system that can have a big impact on pedestrian safety. So for pedestrian-related research, so these are some of the items we have. We are doing pedestrian research related to connected vehicles, related to autonomous vehicles, and even when the autonomous vehicles are not connected, without communication. So we are doing a research now, just using autonomous vehicle sensors, how you can ensure that the vulnerable road users, especially people on wheelchair, can be safe. Because autonomous vehicles might miss, the sensors might miss the wheelchair suddenly crossing the road. So we are using pre-scan, and Metamoto will show shortly, and WeBots, it's a robotic software. So we are using that in our lab, Transportation Cyber Physical Systems lab. And we are also have it connected traffic signals on our test bed. We are using that to do pedestrian safety research as well as other mobility research. So we are working with on artificial intelligence. Currently, we are working a lot on the quantum computing, so quantum AI, quantum artificial intelligence, so that the processing could be quicker, and we are comparing how quick it is compared to traditional computers. Now, in terms of our the mobile devices, we have connected autonomous vehicles. So, and I will show that we have a unique features in our vehicles. So it's research ready, and we have connected vehicles. We have roadside units throughout perimeter road. We have cameras at intersections, looking at intersection, and we have edge computing devices that are running different connected autonomous vehicle applications. So what you saw, we were processing it on the roadside device, but as the number of connected vehicles go up, or we have to use system edge, so we have to process. We cannot process all the data on the roadside. So for DOTs and other public agencies, commercial cloud could be an option to run pedestrian safety algorithms or any other algorithms related to connected vehicles, autonomous vehicles, or any smart city applications. So we are looking at the clouds, application of cloud. So in our case, so public agencies do not have to maintain huge computer system. So they can use commercial clouds to do it. So we are looking at AWS, Amazon Cloud Service, Google Cloud Platform, and Microsoft Azure. So, and right now we are looking at if we use for pedestrian safety or any other mobility application, we have to send data from vehicles or from pedestrians to cloud, and cloud will process the data. This is the cloud layers, software platform, and then you have the infrastructure platform, so how they will be performing in terms of the delay. So the delay includes the data upload time, processing time, and download time, data download time to the vehicle and the pedestrians. And we are finding that it's so it can meet the safety requirements. Like it can be processed very quickly. We are looking at Amazon Cloud, and we are sending data at different times when it's a peak hour, non-peak hour. So we are looking at the time, the delay. The processing is pretty quick, but our research question is the upload time and download time, and what is the best way to use these clouds. So it's very similar the way you will use Amazon, Google, Microsoft. So if you know how to use one for connected vehicle application, so you can use the others. So and then the cloud, we are looking critically the software layer, platform layer, and infrastructure layer in running our applications for connected vehicles, for autonomous vehicles. And also one important thing, so public agencies might be a bit reluctant to use commercial cloud for security, and but we are looking security issues critically, but we have some encouraging result that it will be very secure and safe. So we are doing research on security as well. So if a public agency wants to run their application, transportation application in the cloud, so how secure it will be, how private it will be. So we are looking into that. So this is the latest edition, at Clemson University. We just got an open connected autonomous vehicle. So it's a novel module, open architecture, open interface, open source software-based research instrument. So we have the vehicle, fully autonomous vehicle, Chrysler Pacifica. So it was a gift from Clemson University. So, but we are running, so the autonomous vehicle is research ready, and we are also interfacing with the vehicle with MetaMotor software. So we can do in-the-loop simulation, autonomous vehicle in-the-loop simulation. So autonomous vehicle includes this type of sensors like a radar, LiDAR, and so on, and video image processor. So this will give us an opportunity to do research on our testbed. with real autonomous vehicles. And as we say, it's an open modular, open architecture autonomous vehicle. So it will give us a lot of opportunity to change the application in the autonomous vehicle. So we are very excited with this addition. So this is another research we are currently doing related to autonomous vehicles and people on wheelchair. So right now we are doing, before we go to the real world test, we are doing this in a simulation platform, in a robotic simulation platform. So we are generating AV sensor data, so which is detecting disable, in this case, a wheelchair. Also, we are developing wheelchair motion model, so we can predict the movement of the wheelchair. So say suddenly the wheelchair arrives, tries to cross the road in the middle of, it's not at a crosswalk, but at the middle of the road. So how this sudden, unexpected movement will work when the autonomous vehicles are relying on sensors, no connectivity. But if they miss it, so we are looking at all the ways the wheelchair rider will be safe. So we are looking at that. So based on the prediction of wheelchair path, we are generating a trajectory for the autonomous vehicle so that it can avoid the wheelchair. So the primary purpose is to avoiding the wheelchair. So we are generating the path for the autonomous vehicle so that it can avoid it successfully. So as these are some of the pictures of our daily tests that we do on our test bed. So we are doing pedestrian safety testing, other connected vehicle application testing, as well as security tests. So we want to make sure connected autonomous vehicles are safe. So we are attacking the vehicles, the infrastructure, and we are coming up with ways that our connected autonomous vehicle infrastructures, as well as the vehicles themselves could be safe, secure from any external attacks. So now our latest effort is to build a quantum lab. So we have been working on the quantum AI. So now 5 partner institutions, C2M2, Clemson, Benedict College, University of South Carolina, the Citadel, South Carolina State University. We are working together to establish quantum labs at each of our institutions. Our plan is to headquarter the quantum lab at Benedict College. So, and then we'll collaboratively work together to make our state, South Carolina, a leader in quantum AI research. So we are proceeding, and we are receiving a lot of technical assistance from IBM. So when we are encountering any problem, they are helping us, and we are using their quantum computers. So we are using IBM quantum computers for our research and for our lab. So this is the end of the pedestrian, end of my presentation. So this is a snapshot of our pedestrian safety and mobility research. And you can find more data and more description of how we did the research in this paper. It's published in the IEEE Transactions on Vehicular Technology. So it was recently published, so you can access this paper and find out more detail on the methods and the data, more detailed data. So, yeah. So if you have now the paper, but you still have, look at the paper, but if you still have questions, please feel free to email me later. And if you have some question now, I'll be happy to answer.
So please write your question in the chat box so we can read and answer your questions. So please write your questions in the chat box if you have any question. So there is one question from Brendan.
Yeah.
Do you have a rationale why performance improved for detection when you did compression?
So yes, so the one reason when we did the compression, we actually, without compression, what we saw that we actually did not calibrate our AI model based on, we did not actually calibrate our model based on the weather condition. So, but when we did the compression, so we also retrained the model based on weather condition. So that was the reason possibly that it improved when we did the compression, because we retrained the AI model. So for example, when we ran it for rainy condition, it was running what we did without calibrating for different weather conditions. So that would be the reason.
Any other question? You can also ask question directly if you want. If you unmute.
I think writing down would be good.
Yeah, please write it down if you have any other question. Okay, so there is one question from Fangzhou.
Yeah.
So what's the threshold for time to collision for sending a warning?
So we looked at the safety distance. So how long it takes a vehicle to stop safely. Okay, using like a deceleration. So we assume the speed of deceleration. We followed usually what happens, like what for safety, what is the deceleration rate? So we use that stopping side distance formula and the braking distance. Yeah. So how much, if you press brake, so how long it will take. So that is for connected vehicles which are not automated vehicle. So, but for autonomous vehicle, so it will be same. So how much time it takes for braking to from what speed they were driving at to complete come to a complete stop.
Any other question? Please write it down.
So it's a stopping side distance.
Okay, so there is another question from Dr. Kamat. What filter was used to track and localize the pedestrians? I mean, can you clarify your question a little bit? What do you mean by filter?
So we did the non-max suppression to to make sure that we just include the pedestrian, we don't double count. Is that that's yeah, and then the bounding box, so the way we transform the bounding box, so that was a filter, so we don't double count or we have accurate detection. Right.
So one question from Sakib Khan. So how do you think the overall system will work for an area with high pedestrian traffic?
So it should not matter if it's in a high traffic volume area. So maybe you have to see that the camera is able to look at all the pedestrians coming from in different direction of the intersection. So if you have camera coverage, so with the computational device you have, so the TX2, I think it should be able to run, if you scale up than what we had. So it should be okay, just you need make sure, you have to make sure that the camera is covering all direction. Now, but that's something that if you like in a very busy city, in a downtown area in Atlanta, so we have not done it in in a busy downtown area, but it would be an interesting research to see how it works. But what I know of the method, how it's working, should work well in any environment.
Maybe I can add on this one. So maybe using multiple cameras might be another solution of in case of high pedestrian traffic.
Yeah, that's what I meant. Yeah. Good, thank you.
So there is another question from Israel Elijah. So how was the vehicle identification done?
Oh, so the vehicle identification, So a very good question, Eliza. Thank you that you asked that. So you can also use the video based detection if it is not connected vehicle, right? But in our case, we use connected vehicle. So the connected vehicles were sending basic safety messages like 10 times per second. So they have a radio. Connected vehicles have radio. Each one have one radio, so it was transmitting basic safety messages or broadcasting 10 times per second. So we were receiving those basic safety messages from connected vehicles. So can we, Mizan, show the diagram where we show that connected vehicles are sending? Yeah.
Mm.
Yeah.
Okay.
I think the first. Yeah.
So here it is showing the vehicle is coming and it is sending the information
Yes,
to the
sending information
infrastructure
continuously, 10 times per second. Yeah.
So in this picture,
yeah, here too, I think the experimental setup.
Mhm. And also in the first figure, it is, I think, slide 3.
Yeah.
So we are sending basic safety messages from the vehicle to the roadside infrastructure.
It's directly sending that. But we can also, so for our experiment, we use connected vehicles. But you can also do the same thing. You can develop basic safety messages from video image processors. Like we did pedestrian safety messages for pedestrians. You can do the same for vehicles as well. But in our case, we use connected vehicle broadcasted data.
So there is another question from Sagar. So can this method be applied during night time?
Yes, Sagar. So we did that. We used the different weather conditions, right? The dark. Yeah, it can be used. Yeah.
There is another question from Dr. Calhoun. When computing the latency for sending the BSM,
yes,
is the message send a point-to-point or broadcast?
So from which location to which location?
When computing the latency for sending the BSM.
Yes. So we looked at point-to-point. Our delay calculated point-to-point.
Is the message send a point-to-point or broadcast?
So, but the latency we calculated is from a roadside unit to the vehicle. We do broadcast it because we are using DSRC radio. We are broadcasting the warning, but the way we calculate it is actually point-to-point because we have different connected vehicles. We want to see that it received by different vehicles at different points on the intersection. We meet the 100 millisecond requirement.
There is another question from Dr. Karan. How many connected vehicles can be in the area before the latency increases over the 100 millisecond threshold?
Yeah, so we have not tested so we use a couple of connected vehicles, but we did not flood the intersection with many cars. So we did not do that test. If you have like 200 connected vehicles, what will happen to the latency? We did not do that in this experiment.
But we did, I think, another study, we tested the scalability.
Yeah, we did. Mizan, so we did other studies where we, not for this application, that so if you scale up connected vehicles, what happens to the latency? You want to talk about that a little bit?
Oh yes. So, for example, if you have a roadside transportation infrastructure, and if it is a congested condition, then how many vehicles can be there? So based on that, all the vehicles, if try to broadcast the information to the roadside infrastructure, we measured the latency, and we found for another application, not this application, as Dr. Chowdhury mentioned, so it satisfied the latency requirement.
So it did not overload. Yeah.
For data collection.
And I think we we showed a slide on the heterogeneous wireless networking. Is that somewhere?
Yeah,
So,
yes.
so I can show, like I can explain that this is actually our a major research area. So,
Here.
so
Right.
you see that. So this is the heterogeneous wireless networking. So we are doing network slicing. So we are looking at if you increase the number of connected vehicles. So then how you so you know that your network load will be based on the which base station is connecting to. It could be overloaded. So based on that, we are redirecting the vehicle data to different access points. So we are using a concept called heterogeneous wireless networking to make sure that our the infrastructure is not overloaded, the communication infrastructure. So yeah, so this is to make sure that when you scale up from 5 vehicles, if you go to 500 vehicles, still you will have a guaranteed level of service in terms of communication. So you have a guaranteed communication. So that's what we are looking at. So we are using software-defined networking to actually allocate different access points to different vehicles.
Two more questions from Fanjo. The first question is there any partially occlusion happened when using the camera to detect pedestrian, like by trucks? That is the first question.
Yeah, okay. And the second question?
Second question is for pedestrian with disability.
Okay.
Is there any difference in terms of detection or decision making?
Okay, very good. So Fanjo, thank you for the question or questions. So the first question, that occlusion. So so for this, we did not experiment when there was an occlusion, but that can be easily solved by multiple cameras. So I did for other research, the radar sensor research. So for detection, when you have occlusion, you have multiple cameras, so that if you miss in one camera, the other camera will pick up. So you do sort of verification. So if you have multiple cameras, then the occlusion can be taken care of. So for research I did several years back, development of a radar sensor for vehicle detection. So there was an occlusion, but truck was occluding a vehicle. So I had multiple like a low-cost radar sensors. So at one point you will see that. So if you have multiple cameras, this problem could be avoided. So we just need to the redundancy algorithm. So make sure that if one camera is missing, the other one is picking up the pedestrian. So you need multiple camera. And the second question is very good. So this is now our a major research. So how we can help vulnerable road user. So the wheelchair, for example, the wheelchair motion, so it will be different for than pedestrian. So it will go on the speed will be different. It might go in a, so we are looking at different types of wheelchairs too, to develop the motion model. So that will be the difference between wheelchair and pedestrian, how it's moving. So the speed, yeah, and the path, how the wheel is running. So we are using we are developing real wheelchair models.
So a question from Dr. Harris.
Okay.
So were there any surprise results or challenges during the study?
So the challenges was, yeah, that's a very good question, Dr. Harris. So thank you for attending. Really appreciate it. So what challenge we faced, ground truth location. So because GPS is not accurate, right? So what we establish as ground truth. So that we had to do extensive research on how we can determine the ground truth. So we use the satellite, the 4 satellite based system, as we mentioned. So, but that is also has some problem. So we looked at how to correct that data with different serving equipment and this the OPAS service, right? So that took some effort, and also we got help from our professors, especially Dr. Wayne Saraswat. So he helped us with some resources we used to locate the pedestrians, to find the true location of the pedestrian. So we had to go through some extensive study and use different devices to establish the true location of of the pedestrian. So we can compare with our video-based system. So that was a significant effort.
I think that's all. Still, if you have any question, you can always email us.
Let's show the last page, the article, like, so if you can see that. So because some of the equation, for example, time to collision. So that was actually a very, it was shown as a simple equation, right? But it's not as simple as you think. So because we had to solve differential equations to find the t. So if you want more information, please read this paper. This is a very good, very high impact journal, as you know. IEEE Transaction Vehicular Technology. It's one of the highest impact journals in IEEE, so it will give you more detail. And I'll be always available, so if you have any question, please feel free to ask. That's actually I have to do. So now we are doing this research, so we have to work with different companies, state and other public agencies to install the system in different locations. So yeah, so more questions I have, I'll be more happy. Yeah, it will make me very happy. So if I have questions.
Thank you so much, Dr. Chowdhury, and thank you all for attending this webinar.
Thank you all. Thank you, Charlotte. Thank you, Mizan, for arranging this. Thank you.
Thank you. So I think we can.
Thank you. Thank you all.